So you've brought some pretty interesting sources with you this time.
Yeah.
And we're diving deep into antenna design today.
Uh-huh.
And based on what you've shared, looks like we're zeroing in on the bow tie antenna.
Yep.
So our mission today is to kind of
Right.
pull out the most useful information about this particular type of antenna from the technical document you've got.
Okay.
And maybe see what makes it so potentially powerful in our wireless world.
Absolutely. Antennas are everywhere. Maybe we don't always think about them,
Yeah.
but they're like super fundamental to how we actually connect and talk to each other. You know what I mean?
Right.
And as everything's getting smaller and smaller and we need to be online all the time,
Oh, yeah.
the pressure's on for antennas to be like
Right.
super effective but tiny.
Small but mighty.
Exactly. So
No.
let's jump in and see how the bow tie antenna stacks up.
Okay, so a bow tie antenna,
Yeah.
kind of a cool name.
Uh-huh.
But in the world of microstrip technology, what's that really telling us?
Well, a bow tie antenna is a type of microstrip antenna.
Okay.
Sometimes it's called a hexagonal patch antenna,
Really?
which kind of gives you a visual, you know?
Yeah, I can kind of see that, yeah.
Yeah. And right away, the really cool thing is its size.
Okay.
That small size is a huge advantage because they can just slip right into microstrip circuits,
Okay.
next to other parts.
So it's all about fitting in.
Yeah.
But usually when you make something smaller, there's a trade-off.
Right.
Like a smaller antenna means weaker signal.
That's a good point.
Yeah.
You're right. Traditionally, we think of those big dish antennas as having tons of gain.
Right, exactly.
But the cool thing about bow ties is that even though they're smaller, they can actually get pretty similar gain if you design them, right?
Okay.
So it's all about how that shape interacts with the electromagnetic waves.
Okay, so how do they pull off that magic trick?
Yeah.
Shrinking it down, but still making it work.
Yeah.
What are the key ingredients in a bow tie's design that make it so compact but powerful?
Well, there are a bunch of factors at play here.
Okay.
Let's start with the substrate.
Okay.
Bow tie antennas are usually made with this thin dielectric substrate.
Okay.
It's like a really thin insulating layer,
Okay.
and it's coated with a conductive foil.
Right.
And that's what makes them so light.
Okay, so the substrate material itself is probably pretty important.
Oh, it's absolutely crucial.
Okay.
The dielectric constant of that substrate, which is basically its ability to store electrical energy
Okay.
that directly affects the antenna's bandwidth
Okay.
and its operating frequency, too.
Right.
A higher dielectric constant actually slows down the electromagnetic wave.
Oh, really?
Yeah, as it goes through the substrate.
Interesting. So like a slower wave in the same space means a lower frequency.
Exactly.
Huh.
It's like fitting a longer wave into the same box, like you said.
Interesting.
Think of it like a crowded swimming pool.
Okay.
The more crowded it is,
Yeah.
higher dielectric constant,
Yeah.
the slower the waves, the electromagnetic signals can move through it.
I see. Okay.
However, your source also points out a key trade-off here.
Okay.
While a higher dielectric constant means you can have a smaller antenna at a given frequency,
Right.
it can also make the whole thing less efficient
Oh, how so?
because you lose energy within the antenna's feed network and the substrate itself.
Oh, I see.
Plus, they can become more sensitive to interference at certain frequencies.
Huh. Interesting.
So choosing the right substrate,
Right.
it's this delicate balancing act
Yeah.
between size and efficiency, which is kind of a fundamental thing in antenna design.
Right. You can't get everything.
Exactly.
Okay. So how about the way the signal actually gets into the antenna?
Right.
That's where the feeding technique comes in, right?
Exactly.
Okay.
You have a few ways to feed a microstrip patch antenna,
Okay.
but your source focuses on the microstrip line feed as like the simpler method.
Okay.
It basically uses a conductive strip connected right to the radiating patch of the antenna.
Okay.
It's a pretty straightforward way to get the energy onto the antenna.
And simpler usually means easier to manufacture, which we'll get into.
Oh.
But are there any downsides to that kind of direct connection?
There can be.
Okay.
Your notes say that if the substrate gets thicker with this kind of feed, the bandwidth can actually get narrower.
Oh, interesting.
It's because of these things called surface waves,
Okay.
which are like unwanted electromagnetic waves that travel along the surface.
I see.
And for efficient power transfer, you got to think about impedance matching. It's like if you're trying to push water through a tiny pipe into a big tank,
Yeah.
you're going to lose a lot of water, right?
Right.
Impedance matching is about making sure the pipe, which is the transmitter, and the tank, which is the antenna,
Right.
are a good fit so the signal flows nicely.
So you don't lose the signal.
Exactly.
Okay.
And this matching is often done by tweaking the length of the feeding stub, that little conductive strip,
Right.
and also its width compared to the transmission line.
Okay, so we've got this thin substrate, a conductive foil shaped like a bow tie.
And a carefully designed feed line.
Yeah.
Now, your source also talks about being low profile and the practicalities of these antennas.
Yeah.
Why is that such a big deal in the design?
This is where it gets really cool. Beyond just the pure electrical performance,
Okay.
the low-profile design is driven by a few practical things.
All right.
First, aesthetics.
Okay.
Imagine a huge antenna on like a historic building.
Right. Yeah.
It totally ruined the view,
That'd
right?
stick out like a sore thumb.
Exactly.
Oh, yeah.
So keeping the antenna small and hidden is usually important.
Right.
And it's not just about looks.
Right.
A low profile also makes it way easier to mount in different places,
Okay.
like on the sides of buildings or streetlights,
Right.
even on people's houses.
Right.
You don't need those big clunky mounts.
Right.
And the lightweight, because of the thin substrate and foil,
Yeah.
that makes installation even easier.
Oh, okay. So it's got to be discreet and easy to put up.
Yep.
Now, what about the cost? Your source mentions that as a factor as well. Oh, yeah, that's huge. Your notes say that ease of manufacturing is a big priority
Okay.
to keep costs down and production time short.
Right.
Because if the antenna is a pain to assemble, it takes more skilled workers and more time,
Right.
which drives the price up.
Right. That makes sense.
A simpler design that doesn't need a bunch of customization.
Yeah.
That helps control costs.
Right.
Which ultimately makes the product cheaper to sell.
That's right. Keeps it competitive.
Exactly.
Okay, so let's talk materials.
Right.
The source mentions looking at both aluminum and copper.
Uh-huh.
So why did they go with copper in the end?
They considered both aluminum and copper foil
Okay.
for all the conductive parts of the antenna.
Right.
Cost is always a factor, and in this case, they were pretty similar in price. But copper has way better conductivity, like 61% better than aluminum.
Wow, that's a big difference.
Yeah, and that means less energy loss within the antenna itself.
Oh, I
So
see.
it's more efficient.
Okay.
Plus, they already had copper foil on hand in the lab.
Oh, so that makes it even easier.
Exactly.
Okay, so we've got the basic parts down and some key design stuff.
Yeah.
Now, your source mentions directionality.
Mm-hmm.
I always thought of antennas as sending signals out everywhere.
That's what a lot of people think.
Yeah.
And some antennas are designed to be omnidirectional,
Okay.
meaning they radiate power pretty evenly all around.
Okay.
But single-element dipole and bow tie antennas, as your source points out,
Right.
they're not super directional. They don't really focus their energy in one specific direction.
But I thought directional antennas were important for things like long-range communication.
You're absolutely right.
Okay.
That's where antenna arrays come in.
Okay.
If you combine a bunch of simple antenna elements, like our bow tie antennas, into an array, you can really control the direction of the signal.
Oh, interesting.
It's done by carefully controlling the feed, which is how power gets to each element, or the timing of the signal sent to each one. It's like focusing the beam of a flashlight instead of having the light go everywhere.
I see.
So a single bow tie might not be super directional on its own,
Right.
but when you put a bunch together in a smart way, you can really target where you want that signal to go.
Okay, cool.
Right.
And your source also mentioned adding reflectors to these arrays.
Yeah.
What do those do?
Reflectors are basically conductive surfaces you put behind the array,
Okay.
and they help make the antenna even more directional.
Okay.
They basically block any radiation going backwards
Oh, I see.
and redirect it forward,
Right.
which makes the signal stronger in the direction you want it.
So you're basically focusing the energy by bouncing it off this reflector.
Yep.
Okay.
Yeah.
So with multiple bow ties and a reflector, you can make a pretty powerful and focused antenna system.
Exactly.
Now let's get into the specific designs mentioned in your source.
Okay.
We have a 30-degree angle, a 108-degree angle, and a 120-degree angle design.
Uh-huh.
What did the simulations and measurements tell us about each one?
It's amazing how even small changes in the shape can really affect performance.
Yeah.
Let's start with the 30-degree one.
Okay.
The simulations showed it worked around 10.48 gigahertz
Okay.
with a bandwidth of 1.35 gigahertz
Mhm.
and a return loss better than Natus 10 digiweek.
Okay.
So just to be clear for everyone listening,
Yeah.
a return loss under Natus 10 digiweek usually means you have a good impedance match.
Right.
Basically, you're not losing much signal as it goes into the antenna.
Okay.
Most of it's actually getting radiated out there.
Cool. So for this 30-degree design, what was the gain like?
The simulated gain was about 3.6 digi,
Okay.
but the interesting thing your source points out is that this was lower compared to the wider angle designs.
So it seems like a wider bow tie might give you a stronger signal.
That's what it looks like.
Okay. What about that 108-degree design?
All right, so the 108-degree bow tie,
Yeah.
that one operated around 10.1 gigahertz,
Okay.
and it had a wider bandwidth, 1.9 gigahertz,
Okay.
with a return loss still better than Natus 10 Digi.
Uh,
So already we see it's better than the 30-degree one at
Right.
handling different frequencies.
Okay.
The simulated gain also went up to almost 4 dB.
Okay.
And your source mentions that you could boost that gain even more.
Oh, really?
Yeah, by shifting the radiating patch a bit towards the center of the antenna.
Interesting.
And this design also used a quarter wavelength phase stub
Okay.
to make impedance matching easier inside,
I see.
so the signal flows better.
It's amazing how those little design tweaks can make a real difference.
It really is.
Now, how about the 120-degree design? That's the hexagonal one, right?
Yep.
What are we doing about that one?
So the 120-degree or hexagonal bow tie,
Yeah.
that one worked around 10.2 gigahertz
Okay.
with a bandwidth of 1.5 gigahertz.
Okay.
And it had a much better return loss than the original 70-degree one.
So a wider angle generally means better bandwidth and signal strength, at least in simulations.
That's what it looks like so far.
Okay, now what about the real-world measurements? Did those match up with what the simulations predict? Yeah. For those who don't know, what is that exactly?
Right.
And why is it so important for antenna design?
So ANSOFT HFSS, which stands for High Frequency Structure Simulator,
Okay.
it's basically a really powerful software package
Okay.
that lets you simulate electromagnetic fields in 3D.
Oh, wow.
It's like a must-have for antenna designers
Okay.
because you can create virtual models of your designs
Right.
and test them out before you actually build anything.
Oh, that's smart.
Yeah, you know.
Saves time and money.
Exactly. Your source mentions that it has a user-friendly interface
Okay.
and it can handle really complex shapes
Cool.
and even automate a lot of the simulation process.
So it's like a virtual testing ground.
Exactly.
Awesome.
Yeah.
With HFSS, what kind of things can you actually calculate and see?
Oh, tons of stuff.
Okay.
You can look at the electromagnetic fields around the antenna,
Right.
how much power it radiates,
Okay.
the gain in different directions,
Yeah.
the input impedance, which tells you how well it connects to a transmitter or receiver,
Right.
and the radiation patterns, which basically show you how the antenna sends out power in all directions.
That's really helpful. And I bet the software has tools to help you understand all that data.
You bet. Okay.
Your source mentions a few tools within HFSS.
All right.
There's HFSS chart, which lets you plot how different things change with frequency.
Yeah.
Then there's HFSS Smith,
Right.
which gives you the Smith chart.
Okay.
That's a special graph for analyzing impedance and admittance,
Right.
which is super important for making sure you have good impedance matching.
Right. We talked about that earlier.
Exactly. Then there's HFSS Polar for visualizing the radiation and scattering patterns.
Okay.
And finally, there's HFSS 3D pattern,
Yeah.
which shows you the antenna's radiation in full 3D.
Wow, that's cool. So you can really see where the power is going.
Exactly.
Okay, cool. Now, your source also mentions using formulas to actually build these antennas.
Yeah.
We don't have to get into the nitty-gritty math here.
But what kind of things do those formulas help you figure out in the design process?
The formulas are like the mathematical backbone of the design.
Okay.
They give you the starting blueprint
All right.
and help you figure out the exact size of the antenna
Right.
based on the frequency you want and the materials you're using.
Okay.
For example, there are formulas to calculate the width and length of that radiating patch,
Yeah.
the effective permittivity of the substrate,
Okay.
which takes into account how the electromagnetic fields kind of spill over the edges of the patch,
Interesting.
the height and length of the substrate material,
Right.
and the main resonant frequency where the antenna works best.
So the formulas give you a starting point, and then you refine it using the simulation software.
That's it.
Okay, cool. Now, your source mentions a key limitation of traditional bow tie antennas,
Wow.
their narrow bandwidth.
Yeah.
Why is this such a challenge, and what are some ways to overcome it?
This is a really important point.
Okay.
So as your source explains, bow tie antennas, they work based on resonance.
Okay.
Like there's a kind of like a resonant cavity.
I see.
And because of that,
Yeah.
they tend to have a narrow impedance bandwidth, which means they can only handle a small range of frequencies efficiently.
Right.
And that's a problem because today
Yeah.
we need our devices to work across multiple frequency bands.
Right. We have so many different things going on.
Exactly. We've got Wi-Fi, Bluetooth,
Oh,
cellular.
It's a lot.
It all needs different frequencies. So that narrow bandwidth kind of holds them back.
So if they can only handle a small range of frequencies, how are engineers trying to make them work better?
There are a few ways they're trying to improve that.
Okay.
One is to use a thicker substrate,
Okay.
but with a low dielectric constant.
Right.
That helps broaden the bandwidth.
Okay.
They're also trying things like adding extra resonant elements near the main antenna element.
Okay.
that creates multiple operating frequencies.
So it can handle more at once.
Exactly.
Gotcha.
They're also experimenting with stacked layers above or below the main element
Okay.
to improve impedance matching across a wider range of frequencies.
Interesting. And what about those log periodic configurations I see in the notes?
Oh, yeah, those are cool.
Okay.
They basically design the antenna with a bunch of repeating elements
Okay.
that get smaller and smaller in a specific way.
Interesting.
It's like a fractal pattern,
Okay.
and that helps achieve broadband performance.
So it can handle a wider range of frequencies because of the pattern.
That's the idea.
Cool.
And finally, they're looking into using ferrite substrates,
Okay.
which have magnetic properties that can help manipulate the electromagnetic fields and broaden the bandwidth as well.
So it sounds like there's a lot of active research going on to push the limits of this seemingly simple design.
Oh, absolutely.
It's exciting to see what they'll come up with.
Yeah, for sure.
So with all those potential improvements on the horizon, what are some of the most promising applications for bow tie antennas?
Well, the need for compact antennas keeps growing.
Oh, yeah, absolutely.
So bow ties are becoming really attractive.
Makes sense.
Your source specifically mentions using them in arrays for wireless communication.
Right.
They're small and flat, so they're great for making dense antenna systems
Yeah.
for things like 5G and beyond.
Right.
And they're also being explored in science,
Oh, cool. Like what?
like in astrophysics
Right.
for studying the cosmic microwave background.
Wow.
They need huge arrays of sensitive but compact antennas to pick up those faint signals from the early universe.
That's incredible. So bow tie antennas are helping us look back in time.
In a way, yeah.
That's amazing.
Your source also points out that development is still ongoing. They're
Right.
constantly tweaking and refining the design,
Okay.
so we can expect even better performance and more applications in the future.
It's fascinating to see how such a basic design can be so versatile and powerful.
They really are.
It's a testament to the ingenuity of engineers, always trying to make things smaller, cheaper, and more efficient.
Yeah, without sacrificing performance.
Exactly.
The bow tie antenna is a perfect example of that.
Well, this has been a really interesting deep dive into the world of bow tie antennas.
Yeah, thanks for bringing such a cool source.
Absolutely. It's amazing to see the thought and detail that goes into designing even these seemingly simple parts of our technology.
It really is. And it highlights that you got to think about more than just the electrical side of things.
Right.
You got to consider manufacturing, deployment, even how it looks.
Yeah, it all matters.
Exactly.
So maybe now when you see an antenna out in the world,
Yeah,
you'll think a little differently about how it's shaping and directing all those invisible waves.
hopefully.
All right, well, before we wrap up, I want to leave you with a thought.
Okay.
Given all those trade-offs we talked about,
You're right.
balancing size, bandwidth, and gain,
Yeah.
what kind of future applications might actually be better served by highly specialized antennas?
Hmm.
Antennas designed for a very specific purpose, rather than trying to make one antenna do everything.
That's a great question to ponder.
Yeah, something to think about.
Definitely.
Well, thanks so much for joining us for this deep dive.
My pleasure.
We really appreciate you sharing your expertise and your sources.
Anytime.
Until next time.